Hello everybody, welcome to this video about sensor-based laser micromachining. My name is Albert Bordeman. I'm Managing Director of DEMCON FOCAL, which is part of the DEMCON group. We are mainly focusing on opto-mechatronic systems, especially design, engineering and manufacturing. We are located in the Netherlands, but also we have groups in Singapore and in Germany. And today I want to talk about this, what I call sensor-based adaptive laser micromachining. And I will share my screen so that you show my presentation. On the first slide, you see my email address and my phone number. So if you would like to contact me, please, you're welcome to do so. Share my screen. I hope it will work out properly. Think so. So there we go. These are my details. As you can see, it was part of the Photonics virtual exhibition. Fortunately, it didn't work out, but now we have a second chance. Laser micromachining. Well, as you can see on the left, it is a schematic drawing of such a laser micromachining. Quite easy system. Laser, beam delivery, scanning and data lens, and of course the workpiece. On the right, you see a machine, such a machine that is developed and sold by Leitmotive, which is also located in the Netherlands. We work together with them in Horizon 2020 project. So they make all kinds of nice structures. As you can see on the right, these structures are holes, or pockets. And they normally they produce these pockets, and then they have to offline measure the depth of such a pocket. And then they have to go back into the machine, find their proper position again, and then continue with the process. It's a very time-consuming and not that accurate. And they would like to have an inline measurement system. So we come together in a public funding project, and we thought about this process. It's an OCT-based process, in which actually on the right you see the measurement system, which consists of the broadband light source, in our case, a subcontinuum laser source. It's split into two branches. The signal branch, as you can see over here, the signal branch is going into the system and is actually following the same optical path as the laser system is using. And it goes through all these optical elements and to the workpiece, and then it's reflected again. But there's also another branch, which is the reference branch, that goes through the reference path and is reflected there, and then they are combined and come together into a spectrometer. The spectrometer reads out the interference signal, because you can get all kinds of interference there, and you can do Fourier transform, and then you can calculate the optical path length differences between the signal branch and the reference branch. So this is in principle the whole OCT, low coherence interferometry setup. It's quite a standard way, but there are issues with this one. We introduced two main problems. One, the OCT is using the same optical path as laser beam. And that causes all kinds of aberration, as you can imagine, because the laser beam is a certain wavelength. The measurement system has a very broadband wavelength, and that causes problems. The second one is that during the milling, your reflection is changing. Normally you start with a very shiny surface, but during the milling, your surface will become very dark, and which means reflection will go very low. But if your reference signal is not changed, your interference signal, with this low reflection from the signal, is going very worse, as I depicted on the left. So a huge DC signal and your interference signals is very low. So that is also one problem. And within this project, we try and we solve these two problems. I will show you the results. First of all, the problem of the wavelengths, especially the fact that you see on the left, there's the green one, which is our actually laser we use for the laser micromilling. And we selected a measurement signal, which is the red one, closely to the green one. And we use a very long pass, good long pass filter to separate these two, or else you can get all kind of interference you don't want to have. But also you have all kind of chromatic aberrations, especially in the f-theta lens. And we work together with the company Sil Optics that developed such color corrected f-theta lens that could deal with this broad wavelength ranges. So it works out very well, and we're very successful that both of the whole wavelength range could be covered by the optical path in the laser micromachining. Next one. As next one, you see the reference path. Actually, the problem, of course, is that the reference path, if you do nothing, is always have the same reflection, but your signal is changing drastically. So what we make is an automatic reference path that could correct for the signal changes. So it could measure the signal that is being reflected. Based on that, there is some kind of shutter that could close down the optical path a little bit, so that the reflection of the reference path is also changing. And by doing so, your interference pattern can become very good again. Of course, the total signal level is going less, so you need also need a longer exposure time for your spectrometer. So auto exposure is also needed, and that has been solved by the software. So typical examples, as you can see over here on the left, you see the dark spots, the dark pockets, and these are the shiny pockets. And on the right, you see a typical raw data curve. You have all kinds of shapes in it. We have to solve these shapes, and we have to correct for them. And these are some results, just to show you what have been achieved, just some European stars, nice examples. But most important results are a range of 1.2 millimeters. That's the overall range. The lateral resolution of 20 micrometers because of the spot diameter. Repeatability of 1.5 and 20 kilohertz is the maximum measurement rate. But if you go down with respect to the pocket, it's getting more and more dark. Your measurement rate will drop drastically to 1 kilohertz and below. Field of view is in the order of 20 by 20 millimeters. We integrated that one. I didn't show you the picture, but it has been integrated. And this is a measurement we've done. We used to remove defects on the surface. And this is a typical defect that has been observed on the surface. We would like to remove it. This is a picture of an offline measurement using a confocal measurement method. And this is the same picture using an inline measurement system, OCT system. And this is how the defect looks like. And then we adjust the laser ablation process such that we say, okay, we need such much power to remove that defect. It has been done, adjusted a little bit. We measured it again and adjusted it a little bit, our process. And at the end, we end up with an almost fully removed defect. So it shows that it works. And we are really happy that we are achieved this result, and the total process is in the order of 1 to 2-3 minutes. So that's come to the end of the presentation about the video. These are the partners we work together with. I'm very happy with these partners. Please, you're welcome to talk with me about this issue, also with other things regarding opto-mechatronic systems, design and engineering. Please contact us. Thank you for your attention, and hopefully we keep in touch. Bye-bye. So I'm now stop sharing my screen. I wish you all the best, and maybe we can talk later about this subject. Please do not hesitate to contact. Bye-bye.